Good afternoon, colleagues and students. Thanks for coming to our seminar. Today, I am very honored to welcome Professor Song-Ping Zhu from the University of Wollongong, and I was very honored that he was actually visiting Malaysia, and, uh, and he managed to make a turn to South Africa, in particular because he was my my postdoc supervisor that gave me an opportunity to be in Wollongong University, which I will forever treasure my memory there. And today he's going to talk to us about the price connection between collection option with a moving windows and the fixed windows counterpart. And he is, he's much more into mathematical finance, and he's very well known into pricing, numerical method for pricing numerical stylized option. Thank you very much. Over to you.
Thank you. Thank you. Yes, first of all, don't be frightened by whatever the math I'm going to present in there. I'll cut it down to the minimum math. In fact, I'll choose this subject, this topic, because I actually very proud of the work. I like it. And I'll show you probably the strong connections with mathematical finance and the risk management and so on and so forth. Right? And but first of all, just a very brief correction to myself. I didn't go to Malaysia. It was Mauritius, an African country. Extended trip to come to South Africa. And thanks for his hospitality and receiving me here. I'm quite happy to give a seminar. He wants me to talk about my recent work. Okay. This one, I'll put a title there, and I gave a talk at the University of Cape Town. Change the title slightly. Corporate finance, stabilizing options, with more stronger links with what we do as mathematicians to what people like say knows finance. And today I'll show you a example. I don't know. It looks like there are some students sitting there, and in case you are worrying about the publishing papers and being so hard and so on and so forth. Through this talk, I'm going to show you that it may not be so bad. There are some papers where you have to put extensive effort on math for what I do. But some others, even high school mathematics, might be issue publication, not only publication, but one of the top journals. This journal that they're publishing is one of the top ones in terms of what they call finance practitioners, mainly people who trade, who works in the industry. They do this sort of very, very practical work. So let me tell you what this is. First of all, let me acknowledge that this is co-authored, but joint work with one of my PhD students who's now working in one of the largest economies in Australia. As soon as she finished off, before that, she was also in my area with math background, quantitative finance, very much so. When Matthias starts a program, we call it different names. Some risk management is roughly the same. Once you have some quantitative skills, especially if you pay more attention to code, it helps a lot in terms of job finding. Okay, then I'll probably structure this talk into 5 parts, and then I will spend most of the time on background review and a little bit telling you what the objectives, what I've done. So those first 2, in terms of this third bit, it has quite a few math, and especially with this so-called PDE. PDE stands for it's one special area in mathematics called partial differential equations. And let me also give you a rough structure in terms of quantitative finance or mathematical finance. This can be, in terms of approach, can be divided primarily into 2 camps. One is what we call the PDE. This is small brother, small number of people working on this, including myself, including David. He just asked me this morning to read a bit more and talk about it. That's Carl Trivella, who's also in this camp. The large majority of people in quantitative finance are actually from stochastic stochastic processes. But from that point, so there are two different approaches there. Mainly within this PD approaches, because my background is actually in fluid dynamics and physics. Many people from that area. So then I will also very briefly talk about the documentation discussions. The main thing I want to indicate again the audience here, I want you to see how the paper is simple, with simple math, so as we try to restore the technical. So that's the main thing I want to talk about here. All right, so there is inevitably, I have a bit of math, it's starting to use it's horrible to see this, right? This is a standard one in option pricing. I hope some students you have done somewhere. Says, I assume you understand fundamentally what an option contract is. And then the option contract is fundamental. The breakthrough was 1973 when Schultz came up with a formula. And then later on, it's 1997. That passed away already. This shows and see the impact on society. Millions and millions of dollars from that time to now. Options and trade. It was so hot. That's when the time when I got into this field, it was in 2000. So that's how I attracted into it. The first attraction to me was this equation. This is called the Black-Scholes PDE. The solution of which would be the most famous Black-Scholes formula. I hope you can see it's covered in parts with that. This is the one on calculated V with a simple formula, and then that option price. As I said, I'm cutting from there. I'm assuming everybody knows what option is. Okay. Then this is a phenomenon. Think about it. Let me tell you how I got sucked into this. As a physicist before, I never believed mathematics could be used in social sciences. Social science is so complicated. It's almost impossible. Math is so precise in social science. With all sorts of variations, you can't do anything. But until this breakthrough, and it worked out so well, math somehow merged. Get into the social sciences, find this. And ever since then the usage of math actually overpasses the usage of math in economics. Prior to this, economics was the one that used the most. Anyway, so that's the famous Black-Scholes formula. That's my introduction. And then the one before it, the well-known Black-Scholes formula is actually for European option. And most of my work since probably new is actually for pricing American options. Okay, I assume that talking about it, the American option, one simple way to describe it is that you have to look at the earlier exercise boundary, which is described mathematically by this SFT. That function needs to be solved together with the V function. But previously, the European, there wasn't any SF. In a simple way, that one is related to this early exercise feature. A simple switch. On the contrary, later I'll show you lots of in the rest of my talk. Simple switch, you add a little simple term from being exercised at the end to being able to exercise early from option. Mathematically change it from a linear problem to a nonlinear problem. This is a nonlinear equation. A solution of that was actually my first piece of work in mathematical finance on a series of solution in series form in 2006. And that was paper published a little while. Then, now that's where I use that board. I'm going to talk about some exotic options. Exotic, I'll explain the word exotic means that they're non-standard. One of those exotic options is called the Berry options. Why? What are the Berry options? This is actually motivated by this. Let me just, that's why I need to use a pen. I requested it here. Now, for those who are here, if you're students, I don't know if NITheCS has told you guys about this.
This is I'm drawing a time axis and what we call the underline. Underline, let's think about the stocks over which you write your option, or on which you write your option. So this is, let's say you have a company, there's options written on that company's stock price. So you probably have seen from many textbooks that mathematicians, in order to do something to price options, to actually assume a so-called stochastic processes. Between now, this is t equal to 0, this is now, and a future time, capital T. This is called the expiry time. This time is when an option contract terminates, stops. There are those very long options called the perpetual options. This is an approximation. There's nothing like a perpetuality, infinite. A lifetime is not even infinite. So most of the option contracts would end up at a finite time, say 3 months, a year, whatever, right on the contract. Okay, then between now and the future, this is, if you haven't, I hope you get something from today's lecture, not really on those fancy stuff, but something I want you to get is that one principle people should remember: no one can predict futures. No one. If somebody stands there telling you that he can tell you what will happen in the future, that guy is lying. Absolutely not. Having said that, there are some short-term forecasts you might be able to do using some stochastic statistics tools. That's still within assumptions. There's just stationalities or so on and so forth. I just want to know people who are there's a journal of forecasting. I'm not going to wipe out the entire area. I say no one can predict. I am talking about in principle, no one can predict. Right? So which is why mathematicians come up very cleverly by assuming a stochastic process between now and then. What we have done is to predict an aggravated number rather than the exact option or the stock price at that point. We predicted, we made it in the way of assumption what the average stock price will be or the volatility will be at that point. All right, so that's some sort of prediction, if you want to say that. Yes, that's still there. So this is a debate one time I ended up with my son, who's an assistant professor in the US somewhere. I was telling him that my principle, no one can predict the future. He says, Dad, no. You predicted in your Black-Scholes model in some way, in that aggravated way. That was correct. I took in his argument and I agreed. So anyway, nevertheless, we put in the stochastic process there and to do it. But then again, this is the moment I want to ask if students have ever thought about this before. Let's say you're one of your South African company today with a stock price S naught, whatever you call in South Africa, you call the rent, right? Your currency. Let's say 1,000 rent or whatever your company. Think about a specific company. I'm not familiar with your companies. 1,000 rent today. For stocks, I'm talking about the company's stock values. Let's say this, keep thinking about this one, say example, 3 months. Who would say that stocks would go to infinity at a capital T? I'm not even talking about twice of the price. I'm talking about infinity, from 1,000 rand to infinity. It's impossible, right? But then in that case, I would also ask why in your risk management in Messiah's case, and you put this ST mathematically right in the range of 0 to infinity. We write in that way, so our stock price will vary from 0, which is hitting at the bottom here, to infinity, all the way to infinity. Why would we do that? We know it's so stupid, it never gets there. That is the answer. I know you probably haven't thought about it. The answer is this, right? Because you are using calculus. You're using mathematical tools. One of the most essential features of calculus is to have some special numbers, 0, 1, and the next one is infinity. Mathematicians came up with this. Without infinity, the whole calculus will fall apart. Whole thing falls apart. So that you can view that as an approximation to the reality. Okay, but then the financial engineers now say, well, if that's the case, I don't like it. I know the stock price will not ever get to infinity. Then they put a barrier there, a level B. You put in a contract, because for an option, you have buyer and seller. You would bet that this stock price would never get that level, right? Let's say, let me draw you a red line because you don't know which one. Stock price, it would never get there. You bet. If it did, then you have this sort of thing. This sort of, it's called the barrier. If it gets touched on that barrier, and you have so-called up and out, up and in, down and out, down and in. Let me explain that to you. So up and out means if your stock price approaches from below and hit that barrier, then your contract is out. You don't have a contract anymore. On the other hand, you can also have up and in. It started with no contract, and once you hit that barrier, suddenly you get a contract. Very nice in that case. And then down means the barrier is below, not instead of up. Okay? So when you do that, then the financial engineers introduce that concept in order to combat that problem I told you earlier. The stock price will never go infinities and get somewhere. But that introduces another problem. Another problem is that when this price gets very close to that barrier, imagine I'm moving my pen. Let me say this is getting very close to here. Small gap. Imagine you have a barrier. Let's say right now is 1,000. The barrier is set at 1,500. Okay, just to give you a number. Let's say you're getting so close, 1,400 something, 1,440, 480. So it's getting so close with a small tiny gap. Aha. Then some bigger guys, such as George Soros, he could come in because he has a big, deep pocket. He comes in and manipulate this underlying price. For example, that company he can buy or sell. In this case, would buy and make it touch it. Buying the stock, that stock price would go up and touch it. At the same time, he sets up option contract, so that once it's touched, the barrier option contract, you either go from no option to an option, or you sell an out option, so you benefit from that touch. That's what George Soros did in the 1997 Thai bar crisis. He set up the position and made a huge amount of money. So that way it's called manipulating the market in order to benefit from that. Then the financial engineers say, okay, if that's the case, we'll have another solution to prevent that from happening, or at least make it a bit harder. So what they do is this. They create another term in the contract. So your underline not only has to touch the barrier, you have to go above for a little bit period of time. Usually, the contract will set up a window. It's window size. Let's say, suppose this is 3 months. Let's say window 2 weeks, just for example. So basically what it says is that within the 2 weeks, your underlying stock need to maintain above that barrier, right? For let's say how many days? Within 2 weeks, maybe you need to maintain at least 3 days. You get it? So now there's a window, and within the window, there's a knockout out option, there's a knockout action that will take place. That 3 days will be naturally less than 20, right? So this is then it diverts to these two types of options. And go to the next one. One is called, then I'm going to skip that. It's called the Parisian and the Parisian. Let me explain to you what the Parisian is. The one, remember, the story is right here. So if it goes up, think it's about 20 days, 2 weeks, and 3 days. Let's say, suppose it goes up for 1 day and then came back for that. Then that 1 day, accumulated 1 day above, will be wiped out if you have this Parisian option, the first one. Right. On the other hand, if it goes up and it comes down after 1 day and it goes back again for another 2 or 3 days, 2 days, let's say, add up the 2, gives you 3, and then knockout starts. Now that's called the Parisian. So in other words, the Parisian is accumulative in that nature, whereas the other one is just the clock, we call the reset of the clock. Okay, so that's at the beginning, you may not understand exactly what those exotic options are. Okay, now once we have that, this is the financial engineers who came up with this more innovative ideas in order to combat that problem of what we called earlier touch-on barrier. Then financial mathematicians, we need to come up with a pricing formula to see how we price these type of options. So then this is where I have done a lot of work in terms of mathematical computation of option price of Parisian and then Parisian 2, those two. Then the next story I want to tell you before I go to what I have done is this. I want to share with you how this sort of options can be used in corporate finance, particularly in so-called bankruptcy laws. Right? So in the US, now I don't know about, I'm not familiar with the South Africa bankruptcy laws, nor am I familiar with the Australian bankruptcy laws. The US one, but the rest of them are very similar to the US. US ones have so-called Chapter 11 and Chapter 7. Roughly, Chapter 7 is the one that the company was bankrupt immediately, to dissolve immediately. And then Chapter 11 is the one called, referred to as bankruptcy protection. So your company will be given a period of time, let's say usually 6 months, within which you're supposed to be able to recover yourself. What that means recover is that you'll be temporarily removed from your debt obligations. You could go just trying to make some money without paying off your debt for 6 months. You're protected for 6 months. Okay, but then without going into details, then usually for the board or the directors, shareholders, they need to decide if the company is in trouble, getting close to bankruptcy, which one you're going to go through the court application. Are you going to file an application for Chapter 11? That's how we say it. Or you can file an application for Chapter 7, meaning that your company will immediately decide. If you want a protection, it's still going to cost you, right? But then you have, management has to make a decision between these two. Now this is where the mathematical finance can come. This decision can be viewed as a down and out Parisian option. Down and out, let me now get down to, remember the one I drew above is when you hit above that. For down and out, now you think about a barrier here, which is very close to zero. Your company stock price is already getting very low here, close to zero. Well, you may say that's not low, but just roughly. Okay. So then within this 6 months, now you think about 6 months as your expiry time. So the court is going to grant you a protection period of 6 months from now to then. So you also demand that your stock price will make sure your stocks is not going to be below this barrier for, let's say, over four months of 6 months. You can put that 4 of all 6. It's up to you. I'm just giving you an example over a period of time with another window. Are you with me? So then you can use the option price to judge whether or not right now at this point, whether or not it's worthwhile for you to file Chapter 7 or Chapter 11 in a bit more quantitative way, rather than the CEO of the company or the directors just think, oh, we think so. This is getting to an area called the real options. We use option tools to make risk management decisions in some sort of quantitative way, not precise. It's not going to give you 100% for sure or give you a number that you could rely on precisely, but this is far better than nothing. Okay, so this is where the down and out Parisian options can be used for corporate finance. I'm going to skip those. And this is now I'm going to explain other concepts about so-called hard window and soft window. This is more relevant to the research I'm about to present to you. Remember, the title of the talk is how I'm going to connect Parisian options with hard windows and with soft windows, or their counterpart of soft windows. But let me explain to you what we mean by hard window and soft window. A hard window is the one that is actually it's a moving, right? But here's time, t equal to 0. This is where we are today, and at any time t, lowercase t, at a future time, we don't know though. Right? Then a hard window is the one you count starting from today. You count all those underlines or the stock values that's going back to that picture. going to be above. You see up and out. You count that area. How many days that has been maintained above? You're starting from the window sizes from here all the way to the current T. So the T is moving until there. Right? So this window gets larger and larger. So your risk of being knocked out, if you are there, is higher because this window counts everything in, right? If it's cumulative, this part will be counted in. Are you with me? Until you reach that point. Earlier I said 3 days. So the risk of your options being knocked out is very high because the window is getting larger and larger, starting from 0. On the other hand, the so-called soft window, I'm going to use a green pen, is such that you go from at a future time t, you go back to a fixed window there, let's say by 2 weeks. And this window, the green window, actually moves with this t, going that way. So the window size is fixed. And then remember, for the green, you have to go above it within that window. Some days within 2 weeks that way. So in this way, the green, you can see the window size is naturally smaller than the red, correct? And then overall risk is going to be smaller. Even at a t.0, I know. I just don't know exactly what risk I'm facing, but I know for the green, the risk is going to be smaller. Because anything that happened, this is already gone, this part, by the time you use the green. Okay, so once you have that, then mathematically, again, we still need to price 2 options. One is with the red, the hard window. The other one with the green, what we call soft window or fixed window. That's the fixed. Now, the trouble is that mathematically, for hard window, the one that you only hit the things that becomes larger, that's much harder. Computation of the 2. And that one is much easier. That's why I did all of that before. Then it came down to this. We started looking for a soft window or a fixed window. This is mathematically harder. And that's where the idea came. In my mind, I was thinking, I've been doing this for the last few years or so. The idea was, can I do something? There must be a link between the two. So the assumption is, I have to do something. I can't do nothing. Assuming you have done all of that for the hard window, can I build a bridge? So that once I've done all that, options up and out in your team, once you order, you can build this into a database or some code. And you do the calculation there. Once you have done that, to actually calculate an option with a soft window, should be no effort any further. Is there a question I was asking is there a direct or there is a bridge? Is there a bridge between the 2 sides of the river? That's basically what the idea. And the answer is actually very simple. At the end, I was so happy. I'll come back to this in a minute, show you how I did it. But this is the conclusion. Come back to that slide. So it's a soft window and a hard window joining the diagram. No, it's going to be in a minute. Why there were 3 lines? Actually, I should get rid of all these 2. This is the one accumulated. That was the number 3 days I gave you before. And there's a window size for the J double bar mathematically, right? And then this is accumulated at the time. What's the accumulation is? And the T is the one I told you before. The superscript here stands for soft window. That's the hard window. Right now, we're assuming that this already been done. The calculation on this side. Then at the end, the bridge is so simple. It's just this. You will be given a contract with a soft window, with an expiry time, with the window size, J double bar, and the accumulated at that point, J prime. Then by the time you do that, all you need is use this simple subtraction to calculate the total tenor that needs to be used to plug into your formula for the hard window. That's it. Then the price comes out. So use those 3. This is only 3 new parameters for soft window. Put that into the hard window formula. That I was so excited by the time I realized that was the case. The reason that I had 2 extra lines is because initially we had some other errors. So this is how research was eventually done
keep correcting your errors. We thought we had a couple of other students that made a tiny mistake there. Eventually, again, later on when I go to verification, I show you how we did stuff. So we had a couple of other stuff that we changed too. Not only changed this one line, we changed the two lines. That turned out to be wrong. I deliberately kept them there to tell audience that sometimes you make people correct your own errors. Okay, so how did we now? That was the conclusion. Let me show you how we did it. And I'm not going to, the rest of them, I'm just going to show you a little bit of high school stuff. And I'm not going to go through a lot of mathematics. Okay, this is the same diagram as I was showing there, a bit more formally, but then I need to show you and show what's done. This I'm changing the notation here. I call the B standing for variance. Some in the paper we call the S bar. That's a parameter indicating for the variance. And this is the same S. So that's the point of view is ST. It's T. It's T equal to 0. And this is the current T. Once again, for the window, this is a fixed window. The window length is fixed. For the previous one, a hard window is referring to this one, starting from this point all the way. So what we did was we introduced a new variable, mathematically called the J bar, and the J still calculates all those above the barrier between 0 and the T. In other words, this one calculates as if you were in hard window. For the soft window, we introduce another one that calculates all the accumulation step above the barrier between 0 and the T minus J. Then when you subtract the J minus from that, you get all the accumulation above the bar within that window. I told you this is high school stuff. Anybody, it's so natural. You introduce that. Yep, that's high school stuff, but next bit is the one that we suffer. So we, PhD students, so this is standard. We introduce a stochastic differential equation, the one I showed you. Right? Then, because of that J bar, and this is the pricing exotic options, what usually I'm not approaching it from market point of view. That's at the other camp. From PDE, and usually PDE includes another dimension in the PDE for the extra risk that you're facing. Mathematically, it comes down to this. For the hard window, you would not have this term. The soft window, you would have this new term, J prime. That, as a result, I'm not going to show you the middle equations, but as a result, that gives you a new dimension in your pricing domain. We call it pricing domain. Initially, without hard window, it will be this T and this J. Now you have a J prime, an extra dimension. We're going to solve that PDE within the domain, pricing domain. And then, here's high school stuff. And there are some restrictions of those parameters, making sure that geometrically or financially, one is not greater than the other. By the time you do all those, realize those inequalities, high school stuff, inequalities, then you can cut off the domains, reduce the size of domain down to this. So that's a key. Even those high school stuff is the key leading to the proof. So we get it down, not going to go into details with that. You get it down to that domain with that chunk. It's a variable domain. If you're trying to remember, if you're trying to solve it, it's a lot harder. But I'm trying to build a link. Okay? Then it's nicely coming. Then all I did was trying to build a link. All I did was trying to convert the PDEs with a soft window to the PDEs with a hard window. The paper has been published. If you want to read the paper, you can actually download this in Journal of Community. And so the whole idea is to convert the PDE that governs the price of a soft window. Sometimes I get the tongue crossed up. Soft window back to the PDE with hard window with some sort of change or benefit. We have done this successfully using a so-called rotational coordinates. Again, high school stuff. You will take your coordinates 45 degrees. As simple as that. And it's hard to get that. So it's a training and experience and see maybe that's something you want to try. Okay.
So rotated coordinate, I'm not going to go through details. Rotated coordinates, 45 degrees, pi over 4. Then we're done. Basically, the PDs, pretty much with a little bit more calculation of those inequalities, then you get that. So the two PDs are exactly the same as a proof for this proposition. This is mathematicians. They use the word proposition, meaning that some sort of conclusion, right, together. So the conclusion is that you assume that you have the barrier S bar for Parisian option with a hard window. If you know that already, as I said before, then the soft window price. You easily calculate it. Watch here. This is what we want, a formula what we want. I'm writing that in terms of hard windows price, with that parameters in the middle being replaced by the parameters here. These are the parameters for soft window. All you need is use hard window formula. That's it. The job is done. So that's why the paper was eventually accepted by this journal of derivatives. They have simple ideas, simple results, something people can easily understand. Of course, in between there's some little details, but it's not really that hard in terms of this paper. So, we talked about, discussion. Okay, then, NITheCS probably know this in mathematical finance quite often. He's doing not only empirical studies. For what I do, we do computation, approximation, pricing. So usually, try to publish a paper, they'll ask you to have some sort of verification. Verification, quite often, in other words, people in practice, practitioners, they don't believe mathematicians and derivation. Yes, it could be errors, which is true. I showed you even earlier. I already had some errors. One way to check is use something that always what perceived to be very reliable. In the first companies, is so-called one-power simulations. So you can simulate the underlying stochastic processes, and then you can do that, even though it takes an awful long time to do the simulation, but then you can compare with another numerical solution approach. It's called equal equation approach, which I use a lot. Usually, and see how we were talking about it in the seminar about that, but this one is better. And then we use the direction approach as we did today. And then, the graph matches very well, whereas if I didn't correct our mistakes, I wouldn't have it. And in terms of time, for the equal equation approaches, right now, the one we use our direction formula. Now, let me explain to you. Why did I still use 3.9 seconds? It probably shouldn't be not. The reason is you still need to calculate that price of the hard window in the first place before I can use my formula. The formula gives you no extra time at all. So that 3.9 seconds is spent on calculating the hard window. The soft window, if you use formula, altogether 3.9 seconds, unless if you use the right Monte Carlo simulations, it's about 7 times longer. And you may say, so what? 21 seconds is still short. Not in today's algorithmic trading. The algorithmic trading is measured sometimes by fractional seconds. So people use formula very, very fast. I'm not going to go through those slides about the financial discussions. I'll just go to the conclusion. So first, mathematically, what I made my students found a new formula, a new connection between Parisian options with soft-window counterparts, and financially, you can see that the reason, I want to explain that sentence, what that means. We're saying when we establish this connection. Financially, this makes sense, because when you have a larger window, the risk is higher, but then for the soft window, in comparison with the soft window, you also shrink that window in some way. So there's a balance point that the risk exposure would be exactly the same. And that balance point is what I discussed. That is where that equivalence of the two, that's the balance between two contracts, that be exposed to the same level of risk. Longer window, short window, but measured differently. That's my conclusion. Thank you.
Any question? have one question.
Okay.
You consider barrier option. I think in your case you consider continuously monitored, but mainly discrete monitored barrier option are more popular.
Good point.
Your result, to try thinking about discretely monitored barrier.
Good question. I haven't. There are several reasons. One, depending on the disk, what we saw in reality. Again, this is another mathematical approximation. In reality, all the data are discrete. You don't have a continuous data every. So even every I mentioned earlier, a fraction of a second. That's still discrete in the mathematical sense. It's not continuous. But continuity is like the infinity I told you earlier. It's the most powerful weapon we have. It's also when the discrete interval is small, that is already providing a good approximation. So we don't really want to get into a point of doing a lot of effort with discrete evaluation. However, one of the other papers in mathematical finance with top journals is actually going the other way. The other way in the sense we recognize this discrete data being used in reality, which may, in some cases, may be too far away from the continuity approximation. So what we did there was exactly to find the formula with discrete data, discrete measurement. Right? So but that wasn't in terms of barrier option, that was in terms of volatility contracts, options, futures. So that one is the one you take into discreteness into consideration. Now, barrier options, again, I haven't done it. That would finish it would considerably increase the mathematical difficulty, which is also why they say that some people, they're more brave than I am. Right? They moved into that area already. They do more work, but I haven't seen anything when you already have the complexity of the Parisian feature, American feature, all tangled together, and then also in the discrete underlying. So tangled. This is how we solve the problem in research. We always go from something simple, relatively easier, to something harder. We build our knowledge gradually going that. That I haven't done it. I'm not aware of anyone who has done in this area with discrete underlying. That's what you're referring to, yeah. Discrete measured barrier option. With a discrete measured barrier, without Parisian feature, I hope I explained that Parisian feature with you, right? The barrier option refers to the touch on barrier. That I've seen it, people have done that's relatively easy. Once you add the Parisian feature, it makes it much harder mathematically. Every time when you add one little feature. So not in terms of everything I presented here, I haven't done anything.
Oh, it would be also interesting to look at maybe sort of like Heston type model.
That's again further complicated.
Or maybe Bates model.
You could, but then again, that's a good question in terms of pricing options, right? There's people who are going to different streams. People who are building up new models. I don't. But if you go back and see all those new models, they all started with a vanilla option. The simplest options, because again, as I said, this is research philosophy. You cannot directly jump into something hard. You gotta go with the simple one. You already have complexity on one thing, the model complexity, and you don't want other option features to get into the picture. On the other hand, for exotic options like the one I'm dealing with, we focus on using the simplest model, Black-Scholes model, for that reason. So you don't want everything to be tangled. You do something relatively to address that feature. At the moment, is to address the American options with Parisian and Parasian, particularly with hard window and software. I haven't done that. People welcome probably doing that with what you call the Heston model. That's a bit more fancy model. Stochastic model.
The exotic options in the pricing, is that follow the maths, or does the maths come first and then the
That's a good point. That's exactly I was trying to tell you earlier that for the exotic options, people usually, at least from what paper I read, they try to use the simplest model to address the exotic features first. You address the soft window and hard window, how they could be cutting down the model to the simplest model, without losing the feature. It's like short model. You want to be very fancy, more modern. Yeah. So we pretty much focus on exotic features, the exotic options. Those are formally included. The underlying models included. If you cannot address the exotic features, what's the point? The fancy model with underlying. So we are for the exotic options, after you explore the exotic go fancy models. When I say models, I mean underlying stock price. He's there, and then yeah, yeah, right. At the moment, yeah. At the moment,
because I'm just curious about something. The way we measure the accounting, the number of people. So I'm just thinking about something. If you just increase the relation of two, the way you count,
yeah,
especially in distance,
yes,
high school things,
yeah.
are we going to think of area of use an area instead of using the distance?
That's a good point. Now, it looks like you have at least understood probably 90% of what I delivered. Well done. That's a good point, but that depends on how the contract is written. For two asset price, there are several ways you can write a contract. For the very option of one, you can count the area, you can count individually and then multiply in some way. It depends on how the contract specifies. Inevitably, one of those ways you're going to bump into a problem mathematically is harder than the other. So my suggestion is always start something simple. Again, this is falling into what I said earlier. Why haven't I dealt with multi-asset problems or multi-asset options? I couldn't even do one asset. Right? When I started, how could I deal with multi-assets? You're going to do things step by step. That's the answer to your question. Yeah, please.
I'm not sure can answer this, but how widespread is the use of particular Parisian options in the markets in the world? I assume these are not listed instruments.
It's not. It's called exchange trading. This is not. This is called the over-the-counter option. They're mainly used in real option case, and also over-the-counter. There are two companies involved. However, having said that, the Parisian themselves are not exchange trading. So in terms of popularity, they're very, very not popular at all. However, they're important instruments because they get more and more used by two companies who go do something, particularly real option cases. Having said that, the Parisian features, there are two more to add to your question. One is barrier option itself, touch on barrier, not parity with a barrier feature. That is exchange listed in London that have been heavily traded. Just the barrier itself, without this extra just make it harder. No one knows exactly how to price it. Well, not only practitioners. This is also what happened in year 2008 when the financial crisis came. They just made it too complicated. More and more items being written into the contract. Less and less people know how to price it. Everybody is just guessing what the price should be. So this is the very options price there. Now, the next point I'll also answer the question is this. Some features that are presented today, they are popularly used in some options. For example, Asian options. That's well traded, right? And Asian options has a window. You go back and average stock in that, and that will determine at the end of option price. So mathematically, that feature is exactly what so some of the stuff I'm doing here mathematically can be used for American-style Asian options without too much effort. You could go that way. But then that would touch this button of popularity. Not Parisian option to Parisian option themselves. You know, the popularity is not there.
Okay, so let's thank Professor Song-Ping.
Thank you.
Thank you.